Pre-calculus students, these are your 9.1 notes, sequences and series, a new chapter, a new topic, a really interesting and different one. It's a fresh start for all of you, something brand new in many cases. So let's take a look at it. First of all, some definitions. An infinite sequence is a function whose domain is the set of positive integers. The function values a sub 1, a sub 2, a sub 3, so on to a sub n are the terms of that sequence. If a pattern stops, we say at a sub n, but really what we mean is if it stops anywhere, it's finite. We call those sequences. If it's infinite, we have another name for it, a series. We'll look at that later. So what are write the first four terms of the sequence. The first examples we'll look at are explicit sequences. We'll look later at recursive sequences and how they're the same, how they're different. So first of all, to write the first four terms of the sequence a sub 1 equals 3n minus 2, you could actually almost think of this as being like functional notation. When we say a sub 1, that means 3 times 1 minus 2, or just simply 3 minus 2, or 1. A sub 2 would be 3 times 2 minus 2, so that's 4. And I think you could probably figure out the pattern here. So the first four terms are going to be 1, then 4. If we did a sub 3, I'll put that down there as well. 3 times 3 minus 2, that's 7. And the next one is 10. Those are your four terms. Alright, so looking at number 2, they give us a new sequence. A sub n is equal to 5 plus negative 1 to the n power. Now I'm not going to show I didn't show much work on the first one, but I'm going to show even less here. Let's think about this. A sub 1 would be 5 plus negative 1 to the first, so that's 4. A sub 2 would be 5 plus negative 1 to the second. That's 6. When we go negative 1 to the third, that's 4. Negative 1 to the fourth is positive 1, so 5 plus 1 would be 6. And since it says to find the first 4, I'm done. 4, 6, 4, 6. Just a repetitive cycle. All right, let's take a look at these next three. We're kind of switching directions on these. Instead of finding the first 4 or 5 terms or whatever, we're actually given those terms, and we're working the opposite way by writing the expression. So on number 3, the first realization is that this is a linear relationship. We have a common difference here of exactly 3. That's an important thing to keep in mind. Now, the other thing we have to consider is essentially, where does this start? So I know the first term, a sub 1 is what I'm going to call it, is 2. Now I'm going to write a little function. It's not going to be exactly right. We're going to have to adjust it. I'm going to say that find the nth term. You take the first term, which is 2, and you add the difference, 3, times the number of terms, which we'd say is n. Now that's really close, except if you were to plug in 1 to this function, a sub 1 equals 2 plus 3 times 1, that actually takes you to the second term. If you plugged in 2, you would get 8, which is the third term. So we're basically one term ahead everywhere here. And I'm going to actually, what I can do to fix that is just, instead of making this n, make it n minus 1. And some of you may realize that you could actually simplify that, or some of you may have thought of it even in a little bit different way. And you could have written it as negative 1 plus 3n, or of course 3n minus 1 would be the same thing. So let's take a look then at number 4. This one is not linear. This one is geometric. In other words, we're multiplying by the same thing every time. In this case, what we're multiplying by, it's a common ratio, so we use this r term to represent that. We are multiplying by 3. Others of you may have looked at this and said, you know, it's not just that we're multiplying by 3, but these are all actually powers of 3. Like we have 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and of course we have alternating signs. We'll come back to the alternating signs at the end. But let's take a look at this then. If I wanted to do this, how do I get these 3 to a certain power terms? Well, it would be something like this. A sub n is equal to 3 to the n power. We just keep multiplying by 3 over and over and over. Now, The alternating signs is the issue we've got to deal with. So what I'm going to do is actually put a -1 out here, and I'm going to also raise that to the n power. We may have to adjust it. So here's what I have to look at. Is the first term negative or positive? It's positive. So I don't want this right here to make it negative. So I need to change this so the first term would now be positive. And this is -1 to the second power. If I went to the second term, it'd be -1 to the third power, and that would be negative, and so on. So we can have a sequence that looks like that. And again, I hope I don't overwhelm you with too many different things going on here at once. Just stick with me, and of course, if you have questions, we're more than happy to work with you in class. But I think you'll pick up a lot just by paying attention and taking good notes here. All right, let's take a look at number 5. Now, this is a really interesting pattern. One that's a little bit challenging to pick up. But here's the list I want to show you. 2, 5, 10, 17. What is going on here? Imagine a list of perfect squares. This one takes a little creativity. You'd have 1, and then 4, and then 3 squared would be 9, and 4 squared would be 16. Do you see a pattern here? Each one of these numbers, ignore the negatives for now, but each one of these perfect squares is exactly 1 less than the numbers in our sequence. So what we're going to do is this. We're going to say a sub n equals, and what we want to do is fix this by doing, we know it's perfect squares, so that would be n squared, but we also know that we're adding 1 to it at the end, so we get 2 instead of 1, 5 instead of 4, etc. The only other thing we have to deal with is the alternating signs. Now in this case, we'll again put a -1 out here, and I'm going to raise this to the n power. And that works because this time, unlike number 4, the first term is negative, the second positive, third negative, and so on. This matches. So again, folks, this is a key to understanding the alternating signs. You have to know this relationship. -1 to any even power is 1, and -1 to any odd power is -1. And I should have had parentheses around that one as well. So keep that relationship in mind as you set up your alternating signs. All right, moving ahead. This is one of the most interesting topics to study, and it's not every day that we discuss rabbit breeding in this class. But why don't you go ahead and read through this. Pause this video, read this paragraph here so you can understand what's happening, and then we'll move forward. All right, welcome back. So let's take a look at this. The Fibonacci sequence is what we're looking at. It's something that was first discovered, as it says here, in 1202. It's rabbit breeding. Seriously? Okay, so here we go. So the situation is each pair of rabbits is not mature for 1 month, but then every pair of rabbits has exactly one other pair of rabbits at the end of 1 month after that, and then they keep reproducing every single month. So the pattern looks like this. At the end of 1 month, you'd still have that original 1 pair, and actually I should start perhaps by saying at the very beginning, which is 0 months, and at the end of 1 month we'd still have 1 pair because they're now mature, but they're not old enough to have babies just yet. That waits for 1 more month. Is this uncomfortable for you as it is for me? Okay, but then they have another pair, so now we're up to 2 pairs of rabbits, and then that baby pair is not old enough to reproduce, but the original is. This is awkward. All right, so then we're up to 3 babies. Well, now at this month, not only is the original pair still going strong, but now their first set of babies is also able to reproduce, so 2 more are produced. And what you'll see is you can follow this sequence just by adding the previous 2 terms. So 1 plus, well, there's nothing else there, so that's just 1, but 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 would give us 8, and then that sequence would follow like this. We'd have a 13, and then a 21, a 34, 55, and we would keep going until we get to the 12th month. Now remember, that's actually the 13th term in the sequence we've listed here, because the first month was the beginning point, and the second number 1 was at the end of 1 month. So at the end of a year, we'd have 233 pairs of baby rabbits, probably with lots of deformities too, because it's a really awkward situation there. Sorry about that discomforting topic. Well, let's move forward here. It's time to move on. All right, write the first 5 terms of a recursive sequence. Folks, here's the deal. What you need to know is when you see this a sub k plus 1, that's the key to all of this. That means the term after a sub k. So if a sub 7 is the term you know, and you can use a sub 7 to find a sub 8, and then you'd use a sub 8 to find a sub 9. In other words, you're just using the term before it to find the one that follows. So if I know that a sub 1 is 7, well, they've given me, that's too easy, they've given me the first answer. I know that this sequence starts with 7, and then it would continue on I would subtract 4 from 7 to find the next term. So a sub 2 would be 7 minus 4. So that's 3. I'd subtract 4 again and get negative 1. And I keep subtracting 4. This says to find the first 5 terms, so I'm going to keep going until I find the first 5. Why don't you try finding the first 5 on number 7 on your own? So pause it and then compare your answer. All right, welcome back, folks. You can see number 7, 2, 6, 18, 54, 162. Each term, to find the next term, you multiply by 3. All right, let's keep going. New terminology for you. Factorials. They're really exciting, right? That's why they're an exclamation point. So factorials. In factorial means 1 times 2 times 3 times every number that leads up to n. So for example, 1 factorial is just simply 1, where 5 factorial will be 1 times 2 times 3 times 4 times 5. And then the weird one, just keep this one in mind, 0 factorial is equal to 1. We can talk about that one more if we need to, but it's definitely an interesting one. Okay, so here we go. 17 factorial divided by 15 factorial. Now remember, 17 factorial means that you're taking 1 times 2 times 3 all the way up to 17. I'm actually going to reverse the order on this and call it 17 times 16 times 15 ... times 1. 15 factorial means you're taking 15 times 14 times 13 times all the way down to 1. Do you notice what happens here? 15 and 15 cancels. My 14, there's a 14 in that ... There's also a 13 and there's a 1. Everything's gone except just simply 17 times 16, and I know you probably are a little uncomfortable with that multiplication, but you can handle it. 17 times 16 is 272, so we could really simplify that thing quite a lot. All right, let's take a look at number 9. We have 8 factorial divided by 2 factorial times 6 factorial. So what I'm going to do is think about it this way. I'm going to think of 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or just simply 6 factorial. 2 factorial is just 2 times 1, we know that. And then 6 factorial, I'm just going to leave as 6 factorial because what I know is those 6 factorials will cancel. I'm left with 8 times 7 divided by 2, which is just simply 28. Sometimes a question like number 10 throws people off even though we're using the exact same philosophies that we've used on 8 and 9. N factorial over n minus 1 factorial. Remember, n factorial means you're taking n times n minus 1 times n minus 2 times n minus 3, and we would keep on counting down until we got to 1. So what I'm going to do is just call this n times n minus 1 factorial because it's all the numbers below. Well, that actually works out quite nicely because my denominator here was just simply n minus 1 factorial, so we can lose those terms, and what I'm left with is n. Seeing that I have this horrible habit of talking way too long, I'm going to have to split this into 2. So move on to video 2 right now.